Welcome back. Here's a pretty tricky problem to do with Snell's law, which in IB Physics is part of Unit C3, suitable for HL and SL students. Here we go. This is a problem. We've got a right-angled prism, which is made of glass with a refractive index of n equals 1.5. It's going through air, entering the prism at an angle of 10 degrees and is refracted. And you've got a whole bunch of problems here to solve. I suggest pausing the video, having a go at it, testing your brain, getting down the brain gym, working out and seeing how you get on. It gets proper tricky at the end. Here's a couple of equations to get you started. Pause the video now, try it yourself, or here's the solutions. Alright, so the wavelength of the beam as it travels through the glass. Well, we know we can figure out wavelength using this wave equation here. The trick is to realise that c represents wave speed, and the velocity of a wave changes as it goes through a more dense medium. Frequency stays the same during refraction, but the wavelength changes proportionately. So as the speed drops in the glass block, the wavelength will decrease as well. Okay? The refractive index of air or vacuum, very close to 1. Vacuum it is 1, here it's very close. So therefore, as it goes into a more dense medium, it will slow down. Because wavelength is proportional to the change in velocity, the change in the speed will determine the change in the wavelength, which gives us 420 nanometers. The next problem is calculate the angle of refraction. So we're going to use the first two sections of Snell's law. We're not too worried about the velocity just now. We substitute in our numbers to find so the incidence is right here, first angle. After it's gone across the boundary, it will refract. So the angle of refraction is the second theta there, sine theta 2. Substituting in our numbers gives us 6.6 degrees, pretty small angle. Now, the next one is figure out the angle of incidence on the beam of the side BC. Right? Pretty tricky. What we need to realize is whenever the beam hits the boundary, there should be a normal drawn at 90 degrees, which I've not done a great job of there. But yeah, there we go, animated nicely. The triangle, as we all know, has a sum of angles of giving 180 degrees. So if I add up all of these angles, 1, 2, and 3, I should end up with 180 degrees. Now we already know that the angle between the beam and the black normal line there is 6.6 degrees. So angle 2 plus this little bit here, 6.6. If we take 90 away from 6.6, that will give us angle 2. Angle 1 is given as 50 degrees. Angle 3 is what we're trying to figure out. But it's not really. The angle of incidence is actually this angle here between the normal and the ray. Okay, so the angles are always measured between the normal and the ray, and what we're looking for is in red there, angle I. So running through that second line of the equation gives us an angle of 46.6 degrees. However, like we see now, that angle of incidence we want is going to be 90 minus that, giving us 43.4 for the answer for C. Alright, next up, we need to show that no light will leave the prism. So if it is less than the critical angle, what we should see is the that ray would come out like so, refracting out of the prism. However, if it's greater, if the angle of incidence is greater than the critical angle, you'll get total internal reflection. At the critical angle, it would go right down the medium here. But if I is greater than C, then we are looking at total internal reflection. Alright, so if the angle is greater than C, now at the critical angle, the ray will refract 90 degrees. So the boundary here, the ray will go right along the boundary, okay, following that BC line of the prism. Sine of 90 is 1, so that makes the math pretty easy. This gives us, using the refractive indexes, sine theta 2, 90 degrees, is 1. So to find sine C, that gives us 41.8 degrees. As our angle of incidence is bigger than that, yes, it will totally internally reflect. There you go.